SQL 2012. Let's give yourselves a round of hand. There you go. Woo! Excellent. I love you guys. This is going to be a great presentation. We're going to have a lot of fun today. So this is a deep dive. My name is Bradley Ball, and we're going to get right into this. This is me. I'm not going to spend a lot of time on this because you can find me online. The coolest thing I've ever done is I worked for the Office of the President. I was their senior SQL DBA for a couple years. It was fun, but you were on call 24/7, 7 days a week, and it lasted for 2 years, so I was really happy when that was over as well, but it was a neat honor. And I've got this book that's coming out, Pro SQL Server 2012 Practices, and I wrote Chapter 14, which is the page and row compression chapter. So if you are sitting here in this talk today, you may actually want to pick up a copy of this or take a look at it on Google and read all the free portions and see if it's actually something that you want to add to your library. So a quick warning. Like I told you, I am going to try to be funny. Carrot Top is on there because I said try. We're going to go fast, so I want you to hold on tight. This goes right up against lunch. As soon as this is over, I will stand here and I will answer questions until my flight leaves tonight if you guys would like. So if I'm not able to get up to all of your questions, then see me after this and we will definitely get a hold. We will make sure you get answers. We're going to go deep, so get ready. This is billed as a 400 level talk, but I'll be honest, the way that PASS rated these sessions, I saw it in the guidebook when I got here. If they had given this out, I probably would have gone 500 level because we're going to go a little bit deeper than what they've got listed as 400. One of the tough things is everybody who does presentations, you never really get a scale of here's how you present it. Paul Randall did a really good one a couple years for the MVP Deep Dives book. And so what I did was I take his scale, I'll do an outline of my presentation, and I'll grade things. I'll go, this is a 5, this is a 6, this is a 4, this is a 3. And then I'll do an average. My average was a little bit less than 500 last year for that particular scale, but I think that scale's a little bit higher than the past one. But let me know, because I got to tell you, I read the feedback. I absolutely love the feedback. If you guys go, look, this could have been added to be better, and again, we've only got 75 minutes, so we will be cramming a lot into this. I will listen to you, and I will try and change things or make examples to where they fit something that you would like to see. So please, if you have feedback, give it to me. The door is that way. If after all this warning, you sit there and you go, you know what, I might not be in the right session, you're not going to hurt my feelings if you don't stay here. Past Summit is very expensive. We all traveled from very far away, most of us from very far away, to be here. I don't want to take your time and I don't want to waste your time. So you're not going to hurt my feelings. Like I said, if you want to leave, please feel free to leave. But now let's get going. So why are you here? We want to know what compression is doing internally. We want to make sure that compression is doing what we want it to do. We want to understand the impact. Know thy data. It's not just a phrase. The more you know about your data, the more you're going to know if you want to compress it. Understanding what compression does internally and how it works is going to help you to understand exactly what type of data it is we would want to compress. I talk to people all the time when they say, I went to my database and I turned on compression. That's the wrong way to do things. Compression is like indexes. Indexes are not right for everything. You wouldn't just go, hey, I'm going to put an index on this table and walk away, my job is done. Bless you. At least I hope you would not do that. I hope you would go, well, what I'm going to do is I'm going to monitor this index. I'm going to look at how it affects execution plans. I'm going to see if they got longer, if they got shorter. I'm going to see if they used it because maybe it's a bad index. And I don't want the overhead of that index sitting out there. Compression is the exact same way. There is data that you can attempt to compress, and there are times where people will go, hey, Balls, I went and I tried to compress this table, and it got bigger. Well, that's because normally what they do is they take something that should not be compressed, they attempt to compress it, and we completely reformat things at the record level and at the page storage level. If your data does not compress, that adds additional overhead. So there are times if you turn compression on, you could see your table grow, and then you're going, wait, what the heck? I thought this was supposed to make it smaller. You've got to know your data, and you've got to make sure that you apply it in the correct way. DBCC commands, we're going to use these a lot today. So every now and then I'm going to say, hey, what does this do? Hey, what does this do? Just to see if anybody can name it. DBCC IND allows us to be able to transverse the page mappings for a particular table. Option 1 will always point to a clustered index, or if you're a heap, it will point to the base table pointers. Option 2 starts off with index IDs. If you take a look at SQL Server, you do select all from sysindexes where object ID equals a particular table. If you have multiple non-clustered indexes on that table, the first one will always be 2. The second one will be 3. The next one will be 4. So if you want to transverse a chain for a non-clustered index, you just change that option. You change it to 1, you change it to 2, you change it to 3. 1 is the clustered index or the heap-based table, 2 is the first non-clustered index. We're not necessarily going to be using it that extensively today to go into non-clustered indexes, but we will be using it quite a bit. So that way when you see DBCC IND, I'm just trying to figure out really quick what are all the pages that are related to this table, so that way we can go a little deeper and look at a page. DBCC page. This allows us to actually get the output of a particular page read from memory so we can see, hey, this is how the data is stored. We're going to use this so we can take a look at regular records and most definitely so we can take a look at compressed records. DBCC trace on 3604. If you don't do 3604, all it does is it says put stuff out into the SSMS window for me to see it. So when I say trace on 3604, what's going to happen is when I run DBCC page, I'll actually be able to see the output. If you don't put 3604 on there and just run DBCC page, you'll get command completed successfully, and you'll wonder where my data is. Okay, so here's a data record. When we sit there and we do DBCC page and we start pulling back data, this is what we're going to see. It looks a little bit complicated. We will use DBCC page option 3, which is a very read-friendly option. And that's what we're going to be using for the majority of the time. But a record is made up of the following parts. You got your tag bytes. You've got status A and status B tag bytes. You've got a null bitmap offset, and then you've got a fixed data region. Fixed data is very, very important in row compression, and we're going to get into that in a moment. But everything that is fixed data length, integers, dates, things of that nature, are stored in this fixed data length right here. After the fixed data length, you have the null bitmap. The null bitmap offset actually says, here's how many columns you have between the fixed length data and the null bitmap. The null bitmap doesn't always have to be there. Very interesting thing. If you don't have nullable columns and you don't have a variable, I'm thinking of the variable offset array. If you don't have nullable columns, it's still there, but it's greatly reduced. It grows because you have a null bitmap per column that actually translates to tell you whether a column is null or not. That's all it does to make sure that if you have nullable columns, you can skip this and you don't have to read all the record. A lot of the things when we look at a data record, there were changes going from 2000 to 2005 that are still there and in place in 2008, and 2008 R2, and 2012. There were even more changes that happened in between 2005 and 2008, and they're not very well documented, and they mainly concern the null bitmap and the way that it works. After the null bitmap, you get to your variable offset array for your variable length data. The variable offset array says, hey, go over here and read the variable length data. And it has a pointer to the end so it can kind of loop and go forward as it reads. You have your variable length data right there. If we had some special information, it would be appended to the end of this. If this was a heap, if we had a forwarding stub or a forwarding pointer, it would be at the back of this record. At that point in time, it's actually a forwarding record instead of a data record, but that's the output you would see on DBCC page. Unfortunately, DBCC page doesn't go data record. You can see forwarding stub, and there's different things to say, hey, this has changed, but if you just look at this in and of itself, you might miss some of this. So Paul Randall did a set of MCM videos. Everybody know what the MCM videos are? If you go out, you Google or you Bing MCM preparedness videos back in 2010 when they made the changes to make the MCM program to where you could actually go to Prometric, set up an appointment, and everybody could take it. Used to be a 3-week, $25,000 course that was taught only in Redmond. Now it's offered to the masses, why we see so many more MCMs. He did this video series. This link, which is also in the slides, will take you directly to this particular video, which is on data structures and data structures internals. Probably the best free video I've ever seen for data structure and internals. There's 70 of them. 70 videos. I mean, some of them are over an hour in length, so over 70 hours worth of content. Go out, get them, watch them. You will be better just for having understood the content. Your ears might bleed a little bit, especially on this one when he starts stepping through how you allocate pages, but it's a really, really good one. I had asked Paul if I could use this, and he very nicely said yes, but this is the best way I've ever seen to say, here's how you read a data record. We just looked at the deep part. This is the easier part. You've got your tag bytes. You've got your null bitmap offset, which points to your null bitmap. You've got your fixed length columns. Your variable offset array, which, like I said, points forward to your variable length column, so that way we read. So we've discussed what a regular data record is. Row compression is the foundation of every single bit of compression that we're going to be doing. So it's very, very important that we understand row compression, because once we turn compression on, things will always be row compressed. So row compression reorganizes data at a record level. They're actually not data records, they're compressed data records at this point in time. Their structure is completely different. But the simplest way I can think to tell you is think of the commercials where they're always up late at night trying to sell you vacuum seal technology so you can save a lot of food in your freezer without getting freezer burn. This is exactly what we're doing to a data record. We're saying, I want all the extra space that you had inside of you, and I want to suck it right out, so that way I can make my storage as efficient as possible. An example, if I have a name column and it's char 50 and I put Bradley Ball in it, well, I'm using 50 columns because that's our fixed length column. It's always going to use 50 no matter what I use. So if I row compress that, I've got 38 bytes worth of saving. If I take the number 10, if I've got an identity integer key and I'm incrementing and it's a very low value, I only need 1 byte for 10, but yet I'm going to store it as 4 bytes in a regular record. So that's going to give me 3 bytes worth of savings. January 25th, 1977, if you take that and you store it in date time, it's 8 bytes. If you compress it and you're not using the timestamp portion of it, it's going to save it as a 4 byte. So when you start looking at your data, we're just talking about bytes. But when you think of millions and millions of records and you start going millions and millions of bytes, that starts adding up to gigs very, very quickly. We also get, our variable identifiers were changed from bytes to bits. And there's one of the things that we'll take a look at is as we're identifying what the column length is, we're no longer using so much data. We're actually at a 4-bit level instead of a byte. We've got special handling of nulls and zeros. We don't have the null bitmap sitting within there. We don't have the null bitmap offset, but we are tracking nulls and we do it in a much more efficient way. So what can I row compress? I'm going to stick this up there so you guys can see it. These are all the different data types. The only thing that was added in SQL 2012 was spatial data types. I got a demo on another presentation that I do. I did it for Pragmatic Works. It's up and online there. If you go to my blog, I've got the scripts where you can sit there and run it in 2012. But I'm really not going to get into that so much today. The one thing I want to say about spatial types, the only type of compression that really works well with them is page compression. They are a CLR type, but they are stored in the fixed length portion of a record. And so you would sit there and think, well, there must be extra space associated with them. It's not. They're almost like a variable record that's stored in the fixed length. Depending on how much data you need for that spatial type depends on how large that spatial type is actually going to be. So when you row compress it, you won't see a lot of space savings. If you page compress it, that's where your bang for your buck starts to come in. You'll actually see a lot more benefit with spatial types. So a compressed record, we have a header. We have something called a CD region. CD region actually tells us what the length for everything in our short data region is. And it also tells us if it's longer than a certain length, if it's longer than 8 bytes, you need to go to the fixed data region. I'm sorry, to the long data region. So Paul Randall has another one of these things that's also up there for 2008, but this is how to read a compressed data record. The bit yearly link right down there, again, that will take you to this video, New Data Structures in SQL 2008 R2. Once again, there's a lot of things that have been added since 2008. Since these videos came out, they really don't cover a lot of the things in 2012, but they give you a great foundation to be able to understand what we're doing with compression. We have our header, our column descriptors, CD region, our short data region, and our long data region. This doesn't look very complex, but we're going to dive a little bit deeper because there's actually more to it than that. First, let's do a demo. So, and not only do I have the slide up there about DBCC page, but on several of these scripts, what I've got is a bit yearly link that actually goes to a blog that Paul Randall did when he was still with the storage engine team on DBCC page. That series also covers DBCC IND. So if those commands confuse you at all or you'd like to learn more information on them, go and read Paul's stuff. It's a lot of really, really good stuff. So the first thing we're going to do is go to Demo A, and we're going to create a database called Demo Compression. What I'm going to do now, so everybody know what sysdmdb persisted SKU features does? What this does is this will tell you if you have anything that is an Enterprise Edition feature turned on for your particular database. So if you have a database and you're on Enterprise Edition, and compression is an enterprise level feature, and you've got it turned on and you go, well, we're going to downgrade or we're going to use a DR Coop server, and that DR Coop server, we're only going to go for standard edition for licensing, you'll need to run this. Right now, I don't have any feature turned on in this database that would prevent me from putting it on standard edition. But you'll see in a moment, after we turn on compression, it will actually flip a bit in the header and we will see that compression is now on, and it comes back in this DMV for us to be able to see this is the feature. Transparent data encryption, change data capture. I believe those are some of the other enterprise features. I think there's 2 or 3 more. I just can't remember them off the top of my head. But compression is number 1. So, woohoo, compression's number 1. All right, we're going to create a table. This is a heap. We're using fixed data records right here. Char 8000. So we're only going to get 1 record per page. We're going to blow this up pretty quick. Let's go down here, and we're going to insert 8,000 records. This should roughly give us 8,000 pages. One of the things I want to take a look at, because I was telling you how the bigger your databases get, I work with some folks with some terabyte level databases, and they told me they saw huge performance improvements by turning on page compression. I worked with some other folks that have a couple 100 gig databases, and there are some particular tables that we compress for them just on their reporting side, and they saw huge performance improvements. This is still a pretty small table. Yes, sir? Read side. Excellent question. Anybody know what set statistics time on is, IO? I see a couple hands. Okay, so what I'm doing here is I'm going to get the statistics as we read items, be it logical reads or physical reads, logical from memory, physical off a disk into memory. Set statistic times, it's just basically going to tell us how much CPU that we utilized. So I turn those on, and then what I'm going to do is I'm going to do a select star from the table we just created. I cannot get this to increase for the life of me in SQL 2012, so I'm going to put this over here. So that way we can actually see it. You see we've got 8,000 rows. We had 8,000 logical reads for this particular table. Our CPU time was 62 milliseconds. So SP estimate data compression savings. I'm going to give you a warning with this one. I'm not going to go into it nearly as deep as I do in my other talk. This is the way that Microsoft has for us to be able to estimate data compression savings for a table. It's not bad, but the way that it works is it takes 5% of your database. It moves it into your tempDB. I'm sorry, 5% of your table that you're attempting to compress, moves it into your tempDB, performs the compression operation, and then extrapolates that across the total size of your table to say this is what I believe your compression savings are going to be. My tables are very, very small in this demo database. I mean, we're talking 120 megs. That's nothing. I got a 5 gig tempDB. We're good. If you have a 130 gig table, or if you have a terabyte size table, 5% of that table going into your tempDB might not be a good thing. You might not want to do that during the middle of the day. So there's a tool up on Codeplex, and I don't at all doubt that the folks that put it up there are trying to do some really good things. But what that tool does is you turn it on, point it at your database, and say, tell me how I can get compression savings. And it does this procedure, page and row, for every single table in your database. So once again, well-meaning folks, but a little bit of caution when you use this. If you have a small database, if your database is about 5 gig, 10 gig, 20 gig, you will probably be okay taking 5% of your tables at a time and putting it into your tempDB as long as your tempDB is moderately sized, or you've got enough room on disk. Might not want to do it during the middle of the day, but you'll probably be okay. It's just when you start getting a lot larger in size, this begins to be one of those things you really want to plan for accordingly. So we'll run this, and you can also run this from the GUI. If you right-click on a table, go to Storage, there's partitioning options, there's compression options. From the GUI, if you say, hey, I want to turn on row or page compression, there's a button where you can hit that says estimate savings. What it does is it runs this behind the scenes and then comes back and says this is what we believe your table size will be. So just so you know, the GUI or the stored proc, either way, 5% into TempDB. So for our particular table, heap 1, we've taken a look at it, and here's what our current size is. Here's the size with the requested compression factor that it believes we're going to have. This was the sample size of our table that it actually extrapolated, and this is the compression results that it received on that. Yes, sir? Now, there are things that you could put in here to be able to say only do it for this particular partition. And yes, in that case, what it'll do is it'll just take the percentage of the table per partition. That could be one way to be able to offset if you've got a very large table. If it is partitioned, you could go, I only want to estimate compression savings on this particular partition. But very good point, excellent point. That is a way you could offset that. But yes, you could specify table. You could even specify index, and you can specify partition number on this. So what I'm going to do now is I'm going to use SP space used on this particular table. So that way we can get the size before, and then I'm going to rebuild it. You can rebuild a table. You can rebuild the index. This is a heap, so we don't have an index that we can rebuild. In 2008, they introduced the ability to rebuild heaps. So what we're going to do is we're going to say alter heap rebuild with data compression equal row. If you wanted page, you would say page, and in a moment I'm going to show you can also specify none. If you compress something and you want to uncompress it, it's just that simple. With data compression equal none. So here we go. If you blinked, you missed it. Here's our reserve size before, here's our reserve size after. Now we didn't get quite down to as far as they wanted, but we did pretty darn good. Now if we turn around and we do another select statement from this heap, this is a pretty quick query. So we're not saving the world, one query at a time here, but this is enough for us to be able to see that our CPU time was still pretty low. Our scan count was 1. Our logical reads went from 8,000 to 17. Now, of course, I'm using a set that is optimized for compression, just to be able to show you how particularly powerful it is. Your results are going to vary. But you could still imagine, if you're able to take a table and you're able to reduce it from 8,000 pages to 500 pages, that's huge, especially if you're performing scans against it. And right down here, persisted skew features, you can see now it's reporting compression is on. So if you ever have a question, can I go to a standard level database if I've got compression on? If you run this, anything comes back? No, you can't. You've got to stick with Enterprise Edition. So let's see. So now I'm just going to rebuild this, and I'm going to uncompress it. And you can see, let me go back, that the syntax is just data compression equals none. So compressing something or uncompressing it, just relatively easy on the commands. When we take a look, you can see we uncompressed our table, and now we're back at the size we were beforehand. Yes, sir?
Do you know if that rebuild will redistribute the rebalance your data across your data files?
That is a very interesting question. So, question is, will the rebuild rebalance your database across the data files? The problem that you normally get is with proportional fill. If file allocations are done two ways in SQL Server, round robin, proportional fill. If you've ever heard, hey, have multiple TempDB files and have them all set to the particular size, that's because you don't want one of them to grow larger than any of the other ones. It uses round robin, and that's part of the way that you alleviate GAM contention on TempDB is you say, hey, I can't do file groups, it's all one on the primary file group, but round robin will say use this file group, then use this file group, then use this one. So the question is, if I've got two data files and I do a rebuild operation, will it distribute? The answer is, it depends. If they're the same size, then the rebuild allocation will it will look at it and it may go, if you've got something coming in, you're going to need something that starts to fill that space to the point that it goes, okay, during this particular operation, look at this algorithm and put it over here. I would have to test that out and see. I'm going to make a note on that because that's an interesting one. Theoretically, I could see where you would think that, but part of me wants to go, I don't think it would work like that because rebuilding a clustered index, Paul Randall actually hit that one on SQL Help the other day. A gentleman asked that. I would imagine that a rebuild operation on a heap would work the exact same way with a clustered index, and he said no to that. So, yeah. Well, no, so a rebuild operation will allocate all new pages, but it's going to be where the space is allocated, and if it's marked in reserve on that file already, it'll try and keep it on that file, so when it drops the previous structure, that it keeps it in the same place. So, and if there's, because most data files end up having a certain amount of free space in them anyway, if one of them is larger than the other, it'll stick with that one, because when you get to proportional fill, the algorithms work a little bit differently. But that's an interesting one. I'll do something on that and get that up on the web. Okay, sorry about that. Let's see. So on this one, what I want to do is I want to row compress something for you, but I want to use inchar and invarchar. Does anybody know what inchar and invarchar are and how they're different from char and varchar? Unicode, absolutely, Unicode compression. And so because I've got my collation set to English-speaking characters, what'll happen is I will actually strip out 50% of the overhead of Unicode compression by row compressing something, with the exception of one particular bit which actually specifies the language so we know what level of compression should apply to it. If you go out to MSDN on the data compression white paper, they've got how collation affects per language. Japanese, I believe you only get about 70% space savings on row compression. On Unicode characters, English is 50%, and there's a couple in between. So if that's something that you really want to look at, please go out there, because that'll help you know thy data. If you're using Unicode characters because you've got international folks that you deal with, international languages that you deal with, that could affect what your decision may be of how you actually want to apply compression, or what your expected results could be. But what we're going to do here, we've just made a second database. I'm going to make a table, and you can see I've got a product name of inchar. Now, this is a fixed length field, so this is going to be 500, but it's actually going to store it as 1,000 because we're getting those double bytes for inchar. In varchar, it's variable length, so my product description is going to be much smaller. However, it will double in size because it is in varchar for Unicode as well. We're going to do a primary key clustered index on this. And I'm just going to insert 5 records real quick because this is just going to fill up this one particular page. I'm going to do DBCC IND, take a look at my table, option 1 for my clustered index, and I can see that I've only got 2 pages for this table. We're very, very small. Page, bless you, 277, page 276. To find out the one we want, we scroll over here and we look at our page type. Page type 10 is an allocation page. We don't want the allocation page. We want the actual data page. Our data page is a page type 1. You can also see, we'll get into this a little bit later for allocation units, but this is in-row data. That's very important for us with the compression. So I'm going to take page 276. I'm going to come over here. I'm going to turn trace flag 3604 on. And I'm going to take a look at my DBCC page output. Now, we are not yet compressed. You can see we're a regular primary record. We've got null bitmap, and we've got variable length columns. It reports those things up in the header. We've got all our data, and you can see these 20s, or I'm sorry, these 2000s. The 2000s, this is hex. If you take it and you convert it to binary and then you go over to ASCII, this is just a white space. This is all the empty white space that we have in that 500 char column, that 500 inchar column that we declared that we're not using. So if we take a look at this, we can see a couple interesting things. Slot. Does everybody know what a page slot is? When you store data on a page, what happens is you store it in a zero-based array that actually points to the records on the page and says, this is where I'm being stored. So your slot array starts off on slot 0. So if I have 750 records on a page, I'm going to have 749 slots. And each one of those slots is going to say, this is where this record is. When we come in and we take a look at it, SQL Server is going to say, I need this particular record. It'll have a pointer so it knows what slot it needs to go to. So we're at slot 0. That's just the first record that we're going to come to on the page. Column 1, we've got a length of 4 because it's an integer. We can see here's our value. My ID equals 1. Let me zoom a little bit on that. And then slot 0, column 2, we can see that the length is 1,000 and the physical is 1,000. And our column name, product name, and it equals sum product 1. Remember, we're 1,000, not 500 because of Unicode. And then we come down here to product description. Here's a generic product description 2. Our length is 76. So we can accurately sit there and go, okay, this is 38 characters. So let's go ahead and compress that and take a look at how that changes this. Now, here's one important thing. I'm going to copy this up here. I want you to see this before and after because we were just discussing this. When I rebuild compression, I get a whole new set of pages. We are literally moving from one data structure to another. Think of it like moving apartments. We just packed up all our stuff and we're moving to a smaller place. Literally going across town, our page numbers change. Our allocation unit changed, our data page changed. So 278, and I'll come over here and look at the data type page 1, and that confirms what I want to do. So I will go back over here. I'm going to put that in DBCC page, and let's take a look at how it changed. You can see we've got this CD array starting to pop up right away, right down here. And then here's our record, and it is a lot smaller. I'm not going to have to scroll very far, as a matter of fact, to get past it. It's still right here. And so here's our data. So slot 0, length 4, physical length is 1. Column 2, 1,000. Now we're at 13. Now, this is only 12 characters. Remember, that extra byte is to tell us about the language option that is being used. Slot 0, column 3, 76. We're at 39. Remember, half of 76 is 38, but one extra bit for language. So we just shrank this record quite a lot on page. And what I want you to see is, for row compression, this is only good as long as we actually have space savings within this page. If I decide I want to bloat this record, all of a sudden, row compression isn't going to save me a whole lot. As a matter of fact, this is when I'll start to see overhead on it. So if you have a varchar max column and you're actually storing 2 gigs of text in there, trying to apply row compression to this is probably not something that would benefit you. Know thy data. So I'm going to use the replicate feature, and what I'm going to do is I'm just going to take and I'm going to replicate A 499 times, B 999, and I'm going to put an integer in there as well. DBCC IND, our pages didn't change. We're still at 278. We were just adding data, no rebuild operations. So when we come down here, now you see there's a lot of extra white space. It's all taken up. I'm sorry, it's not white space, it's actual data. But row compression obviously isn't going to get me much of what I need, except for English Unicode. Because when we come down here and we take a look at this, we'll see slot 0, column 2, we stayed the same because it's a fixed length value. I really couldn't change that unless I wanted to change the identity increment or put something in there just to manipulate it. But right here, 501, let me switch to bars because those are prettier. But the length is 1,000. Down here, the length is 2,000, but our physical is 1,001. That extra 1 character becomes a little bit more obvious at this point in time. But for Unicode compression, we're actually still saving something. So varchar max, there are multiple reasons why you wouldn't want 2 gigs of data to compress it that have nothing to do with this. It's more with allocation units. But if you had something that took up like a char 8000, was actually using all 8,000 characters, you wouldn't see row compression savings. But if it was in char, you could possibly see some row compression savings. So you guys have a pretty good understanding of row compression at this point in time. I would say that we are definitely safe to move on and take a look at it just a little bit deeper. Because one of the things you need to understand is why we see our CPU overhead, especially for row compression, because you see CPU overhead for page and for row compression. That's because when you look closer at this, we have subcomponents inside of these regions. We have our CD region that points to our record and says, here's what the column length is for the short data region. And if it's a long data region, it just identifies that it needs to go somewhere else. The short data region also has data cluster offset arrays and a data cluster. It groups things in clusters of 30. The long data region has an offset array as well as a data cluster offset array and long data itself. Remember, each one of these, it's into how many columns actually fit in this particular portion. The offset array has headers, a number of entry, offset entries, and that points to the number of entries in an array which point to the data cluster. When you start to look at the internals of this, you start to see, okay, there are some things that were actually used as advances go into SQL 2005 to make it more optimal to read certain specific records. That was not lost on us. What happened is we took that internally and we used that to develop a more efficient structure. But how does this actually apply to us? How do we actually work this? So what we're going to do is we're going to do a demo. But in order to understand this demo, I got a little bit of a visual aid that we'll go over before, and maybe we'll do this one more time after, so that way you can see where I'm going with it. Because what I want you to realize is that when I say that it has clusters of 30, it doesn't go, oh, here's the first 30 fixed length columns. It actually matters for all the columns. So if I have 10 columns that are short data types of 5 bytes each, and I have a long column that's 50 bytes, and I only do 2 of those, and I say 10 short columns, and then I do 2 long columns, and then I do 10 short columns, I do 2 long columns, and then I do another 10 short columns, all that blue is going to end up in one particular cluster area. All that green is going to happen in another cluster area. So that means that as I read things, my data cluster offset array for my short data region will only have 130 characters in it. And the reason, because you take 5 for the short repeating rows, and you take, let's see, we've got 20, we got 6, multiply it by 5. It will jump forward and read that data, and then it will go to our long data region, where we will have another cluster offset array for these 2 values, where it will read this. And then you've got your data again that will point to the end of this. So that's actually how this record will be read. But this is very important to know, because this is the way that SQL is reading things behind the scenes. And the deeper you get, this could lead to some confusion. Let's see, so all right. So the first thing we'll do is we'll take a look a little bit closer at this CD region, because I just told you what it's going to do is it's going to track the length for us. So I'm going to insert multiple columns so that way we can see what the different options are. I'm going to insert some data just specifically for that. We'll do a DBCC IND to get our page number, 3604, and then we come down here and we put this in to our DBCC page. We get back here, you can see here's our CD array. You can see this is what it's tracking. This information right here. Let me do this one more time. Cut this off a little bit. Here's column 1, column 2, all the way to column 12. You can see this particular code right here. We've got 1 byte for empty, 2 byte short, 1 byte short, 2 byte short, 3 byte short. And then when we get to a long column, it's just an A. And then a bit column is a B. There's another 2 or 3 bits that are not used, and then there's one that's used for a page dictionary lookup item. But the important thing to know is how this is stored. And when you sit here and you start taking a look at this, so let's see, we've got 12 columns. Each one of these are a byte pattern, which means each one of these is 4 bits. So when we talk about the 4-bit column descriptor, what you can do is you can look in this particular area right here, and you can actually see these descriptors. Here's our A for our long column. Here's our B for our bit. You've got to flip these pairs to be able to look at them correctly, but this is the way that the data is actually stored. This is the way that it's actually being read, is it's looking at these values to know this is where I've got to go for this particular data before I seek it. So one of the things that it led me to believe when I first started learning this, and I learned about these data clusters, you always hear, well, it doesn't matter how you structure your table. The only exception to that is if you have variable length fields at the end that are always going to be null. They might not show up on the variable length array, and it can make your storage smaller. Excuse me. So for this, what I started thinking was, well, if I'm hopping back and forth between short and long data clusters, does that add overhead to the read on my tables? Should I be architecting my tables differently? I originally had that question, and the answer is no, but I want to prove it to you so that way you guys go, hey, I know how this works, but I'm not confused by it. Because that's the thing is, when I first read this, it led me to believe, man, I should go to my data architect and I should say, look, when we're planning this data warehouse and we know there's going to be terabytes of data, this is how we should build this table out. I thought I had found something big. I talked to the Microsoft guys. You would have to, and I played around with this, you would literally have to almost make 1,024 columns and have to hop every single time to really get this to the point that it would start to matter. I mean, it would have to be a crazy wide table that's constantly going back and forth. You could see something with it, but it's so far out of the realm of normal possibility that you won't normally. So what I did, just to make sure that everybody would have a warm fuzzy of, hey, I know what row compression is, I know how things are stored on a record level, and I'm not confused by it, I'm not changing the way I architect my tables. I made this particular example where I take that column, just like we had that slide. I'm going to do 10, 2, 10, 2, 10, 2, all the way over, and I'm going to do this 2 data clusters, and we're going to do some selects from them. Now all this code is out there. I'm not going to walk through that just because it was a really ugly table to build and it was a really ugly insert operation to build. $276 is our page. And when you start taking a look at this, this is that CD region that we were just looking at, right? You can see 1 byte, 5 byte, short, 2 byte long, 5 byte short, 2 byte long. So we've got our alternating pattern. You can see here's our data right there. You can start to see some of these clusters in the different arrays as it's looping forward, because you'll be able to take those as hex values and convert them to decimal and say, oh, here's the particular length that we've got that we're pointing to. And then here's all our data as we see it. So we can actually look at this and we can go, okay, I can see how this is identified by cluster. And the most important part is when you look right here, you can actually see that we transfer from cluster 0 to cluster 1 right here, right in the middle of our 10 bytes. So it's exactly at the 30 column line. So what I'm going to do now is I'll take and I'll actually make a table where we do this. And what I've done this time is I've organized one where we're splitting everything, and then I've got everything where all the long is on one side and all the short is on the other side. And I'm going to put 5,000 rows of data into each one of them. What we'll do then is we'll take the set statistics IO and the set statistics time, and we'll take a look at these just to compare the two so you can see that it's within the margin of error for the optimizer for scan operations, that we don't get any benefit whatsoever from reorganizing or re-architecting our tables. So, new window. And thank God for Zoom It. So you can see 287 milliseconds. And this is on table 1, which has our gaps in it. And then you can look right down here, 263 milliseconds. This is the one that's architected. So the first read you might go, oh, well that was quicker. If we run it again, 273. 266. Back over here. No. Oh, no, I just recreated the table. Okay. So you can take this, you can play around with it, but what I want you to see is just because you've turned compression on, just because you understand it very deeply and internally, and you know exactly how it's going to store stuff, and you know how CPU overhead is, don't freak out and think, oh my God, we've got to go back and re-architect all of our tables. The first time I gave this talk, somebody actually said that to me. They were like, oh, there's a cluster region. Oh, I need, no. Everything's okay. Leave everything the way it is. If you get savings from compression, you're doing good. So I would say at this time we know row compression well enough that we can finally move on to page compression. How are we doing on time? Doing pretty good? Yeah. All right, so what is page compression? Page compression is a superset of row compression. Row compression has all the data stuff that we just covered, but page compression has column prefix compression and also page dictionary compression. I get sick of standing up there all the time, forgive me. It's a lot easier to be able to talk with you guys and see your faces. So what happens is, bless you, it always happens in this particular order. Row compression, column prefix compression, and then page dictionary compression. So those are the three things that always happen for page compression. It alters data at the storage level. And the nice thing is it happens at the binary level, so it's data type agnostic. So if you fit on an in-row data page, you can be compressed. So you don't have to worry about what your data types are when you're working with page compression. That's only for row compression. Row compression is still important to know, though, just because whenever you have an index, everything above the leaf level only receives row compression. Even if you turn page compression on, your index is only going to be row compressed. So that's why I said once you turn compression on, row compression is the base level. You are always going to get it no matter what. Page compression is not quite the same, but we'll get to that in a minute. So we're going to pretend that Microsoft isn't outside with their cat team and we don't have a whole bunch of MVPs, and this god ugly blue and yellow monstrosity is what a data page actually looks like. So what we're going to do is we're going to walk through what page compression is, because I don't know about you, my binary is a little bit rusty. I like to break it out occasionally, but it's a lot more fun to actually understand things. So this is a page, and we've got our page header. When we page compress something, the first thing we're going to do is row compression. Wonderful, we're done. All the extra space is now sucked out of this page. So now what we're going to do is we're going to do column prefix compression. To do column prefix compression, what we're going to do is we're going to go down every single one of these columns, and we're going to say, I want to look at a matching pattern. I want to find what the matching pattern is, and I'm going to take and I'm going to put that up in my anchor tag. Now looking at this first column here, Chad 2004, Chadwick 2010, Chadster 2010, Chad 2005. Our obvious pattern is Chad. So what will happen is we will actually pick the longest record that is in this particular page, which is going to be Chadwick 2010, and we will move it up to our anchor tag. We will null this out, but it's the special handling nulls that we were talking about earlier. We're talking about the bits instead of bytes of information to store a null. So that way, we don't need to store this twice on this page. We just need to have a pointer, which is going to be one of those fancy CD tags that says, go up to the top of the page and get this information if you need to read it. We're going to take Chad 2004 and change it to for 2004 because we've got a pointer that says, hey, if you need information from this, go up here and just get the first 4 bytes of information. So for stir 2010, for 2005. So now let's go ahead and fill out the anchor tag for the rest of the way. When we look at the next column, 35.95, 35.76, 35 point, that's going to be our matching pattern. So we're just going to say, arbitrarily 35.96. That's the one we're going to move up into our anchor tag. The next one, it's basically got the same thing going on. 24 point is our matching pattern. We'll put that up in the anchor tag. And then the last column pretty much has the same thing going on that the first one did. Bradford 2009, that's going to be the value that we'll move up to the top. So we're going to null this out. Now this next one, 42.25. This did not have a matching pattern. This is where some of that overhead starts to come into play. I need to know that there's nothing to actually read for this particular record. So I'm going to put a 0 in front of it. I don't need anything from the anchor tag, but I have just added bytes to the actual record as it's stored on a page because that particular portion of that particular row, I need to know, don't go do anything up in the page header for it. 376, 07584. I'm going to null out 2495, a 0 for 8234, 376, 0 for 7634, and then we're going to take and we're just going to apply it to the last row. So congratulations. We have now applied row compression and we've applied column prefix compression. Yes, sir? Yes, absolutely. So now let's apply page dictionary compression. Now, remember the Sesame Street song, one of these things, not like the other one of these things doesn't belong? Very similar to that, except we're playing the matching card games. I want to find matches. When I find a match, what I'm going to do is I'm going to take that pattern, I'm going to stick it up in a zero-based array, and I'm going to say, okay, this value is up here. If you need it, go get it up in the anchor tag, and I'm going to save as much space across the page as I can. I'm going to do matching patterns of 2, but if I was able to fit more on a screen, I could do 3, I could do 4. When it finds a pattern, it'll take that pattern and it'll move it up in the top of a page. So just because I'm doing 2 here doesn't necessarily mean 2 is all you get. So the first thing I'm going to find is 2004. It's got a match right there and it's got a match right there. So there's a 0, there's a 0 for my multi-dimensional array. I would read that particular part of the pattern. I would say 2004. I would know that the 4 needs to go to the particular column. Don't worry about that. Even though it's just a 4, there's special information within the row that says this is the row I'm in. This is the matching pattern that I need to get for that 4. 4 stir 2010. That's the next thing I come across. So that's going to be a 1. And the one over here on the bottom of the corner, that's going to be a 1. So my next common element, 4 2005. That's going to be a 2. That's going to be a 2. And my last matching pattern on this page is 376. It's going to be 3. That's going to be a 3. Now, if you look at this page, and you think about the page that we originally talked about, you can see that this is a wildly different format than what a regular page looks like, even just a regular page with row compression on it. When we talk about the CPU overhead for page compression, this is where this comes into play. So some page compression gotchas. Non-leaf level indexes always get row compressed. We just talked about that. Pages only receive full page compression if you can have 20% space savings on a page. So if I go to my page and I go, hey, I'm going to page compress you, I'm applying compression, a compression attempt will be made, but it might not succeed. If I can't save at least 20% space savings on a page, it's going to go, you know what, I'm just going to leave you in a row compressed format. There's no way to set that. There's no way for us to tune that. That's an internal mechanism. SQL is going to say either I can save the space or I can't save it, and it'll make the decision. Pages only fully compress during a rebuild on a heap. If you've got heaps and you want to compress them, and then you go in and you insert a lot of information into them, they only insert as row compressed data. Even if you get, because we don't have page splits in a heap, remember, we end up getting new pages allocated to it. We get forwarding pointers, no page splits. So on a heap, you can only take advantage of page compression for inserted data when you do a rebuild operation. Page compression calculations are only fired off for page splits on clustered indexes. If it's a mid-page split, if it's an end-page split, mid-page split, if you insert variable length data and all of a sudden it kind of grows and I bump somebody else off of this page and there's a page split that occurs because of that, that's a mid-page split. Page compression attempt will occur. If I have an end-page split where I'm just inserting new data and the clustered index grows, at the point in time that the page gets full, row compress, row compress, row compress, row compress, split operation, I'm going to try and page compress it. If I can page compress it, then I'll keep inserting data on that page until I need to do another split operation. Page compression attempt. Can I get more space savings? Nope. Okay, new page is allocated. So now let's take a little bit closer look at page compression. Yes, sir. Yep. It rebuilds all the pages. It's like rebuilding an index. At least from an allocation standpoint, it's like that. Let's see, 3. Yeah. Absolutely. Absolutely. I don't have a demo for this particular thing, but it would be pretty easy to mark up. And that's an interesting concept. You know, I'll probably write something up on that. But yes, if you take and you create a table, you apply page compression. If you take a look at the DBCC page output of that, as you're inserting records, they will only be inserted in a row compressed format. At the point in time the page split operation would occur, the page compression attempt will fire, and if that can save space, then it will, and you will not get another page. But at the point in time that the page compressed page becomes full, then you'll get a split operation, and we will do something similar to that right here. Yes. Okay, so the fill factor, it will, but only on rebuild operations. So if you rebuild a clustered index, it'll set it at 80% fill factor. But if you start growing the records in that particular page, like if you have a variable length field and you say, you know, it's a 100 length field, but it can actually get up to 500, and I go in there and I start updating stuff, that record will grow on that page. It will only cause a page split operation when that record grows to the point that it would push something else off. And that's a mid-page split versus an end-page split. But whenever it's a page split operation, regardless of what type, it will attempt a compression operation. Great questions. All right, so, I'm not using my database. There we go. Master didn't like my naming convention. Okay, so I'm going to create a table. We're doing inchar again, so that way we can get the row compressed savings out of that. And I'm going to do 5 records. Now we've looked at this before internally, so I'm going to spare you looking at the DBCC page for the row compression. Let's rebuild it with row though. We know we're going to get a different set of pages. Now if we take that and we bloat that, just like we did in our last example, we're still getting a little bit of space saving from Unicode, but we're at the point now where our pages have really, really grown. So if we do a DBCC IND, we can still see that our data is small enough that we only have one page, and we are a clustered index. But, let's see, I don't need to do a DBCC page. Let's add a couple more records to this. And what we'll do is we'll force a row compression page split. Now this isn't going to do a compression operation yet because we have not yet turned on page compression. But if I do a DBCC IND right now, you can see I've got more pages. If I come over here to my page type column again, you can see my page type 2. Page type 2 is a non-leaf index page. You can tell by the index level how high up it is. So indexes are stored in B trees, and as soon as you split pages, you automatically get a root level. And as you get more and more pages, that hierarchy kind of grows. Think of like a chain of command from the military, or the way Moses had it in the Bible, where there's one figure on top and then there's multiple down. That's basically what our B tree structure is. So in this particular case though, because we only have a very small number of pages, we only have one index root level page. So you can see that we did a split. Now if we rebuild this table with page compression and do another DBCC IND, we see we're back down to one page. Still a clustered index, but we don't need that root anymore because we can fit all of that data on one particular page. So how many records do you think I can fit on one particular page if I optimize my page compression? Just looking at some overhead, about 373. Take a look at DBCC IND, you can see, I took a look at that page, I had about 8 records on there, 373, so about 381 records, and we're still on one page worth of data. So if I take a look at that, and that was 276, you can see, oh, did I get the right table? 276, compression internals 2. There we go. Oh, looks like I already split it out. Never mind. I've still got one. Let's take a look at how many I could fit on there. If I take a look at that, my slot count should tell me 281. $346 I could fit on this particular page. If I scroll out, you can see there are a lot of records sitting on there. So if you have repeating patterns in your database, if it is something at a binary level that looks the same, you will get a huge advantage from page compression. All right, so next up, so where does compression happen? Yes, sir. Yes, as a matter of fact, there's a bulk insert white paper, and one of the things they talk about is if you're going to bulk load a data warehouse, what you could do is you could uncompress things, put it in, and then recompress it, because you can actually time the compression operation, see how long it will take. That would be a situation where my recommendation would be uncompress, insert, recompress, but it would also be something that I say, hey, let's take a dev environment, and let's do a test on this and let's time it out and see if we get an advantage off dropping this. Because I've seen times before where I was surprised where dropping things, making it a heap, inserting stuff into it, but then the amount of time it took to rebuild the clustered index or the other indexes and apply compression on top of that, that was actually longer. I mean, it's always quicker to insert data into a heap. It just flat out is. I had one where we were inserting millions of rows of data. I think it took us like an hour and a half to get it inserted in this particular table. We dropped the indexes, made it a heap, 52 seconds. Matter of fact, I had to go in and do a page count because the guy was like, that didn't, no, 52 seconds, that didn't. It was 52 seconds, but to rebuild all those indexes, it actually took us over an hour and a half. So when we looked at the amount of time to drop them, then to add it, it was actually quicker for us to do the bulk inserts and just leave everything in place. So I would say test it out because it really could depend on your system. Yes, sir. So the only logged operations for page, and I've got a demo for this later, but the only logged operations are page compression attempts. And when you're rebuilding, doing a rebuild operation, so if you restore from backup, if you do something like that, you're not necessarily going to have fragmentation because you're all written out to the disk. It's not going to go, oh, you were scattered before, I'm going to scatter you now. If you're looking at, so the thing to keep in mind is everything that you need to be able to restore, that's how write-ahead logging works. So when you rebuild a page compressed table, if you do it as an online operation or an offline operation, there's going to be a certain amount of logging there, but there's not extra logging. And as a matter of fact, the amount of logging will probably be less as long as you're getting a good compression sample from that table. I've actually seen, because the information that it has to store to be able to put the write-ahead logging out is also in a compressed format. We'll do an example with VLFs where I rebuild a table using compression and I look for the compressed operations, but one of the things we can do is you can go out and look at a column and that DBCC page hex output that we've been looking at, that's in there because we don't take the dirty pages and flush them out of the buffer pool. We do write-ahead logging and that's where that record is stored. And so you can actually see transaction log use decrease because the records that it has to store in the VLFs are actually in a compressed format as well. Some of the information is. Well, right, it's going to have the operation and it's going to have the allocations as it needs to, but you're not modifying those records. So you're just rebuilding them. So we got to log the allocations. We don't have to log, here's what's in each particular table record. Yes, sir. Inserts aren't nearly as bad as you would think. Updates are, and we will get to that. I've actually, but if I was doing, again, it depends. If you're going to bulk load something, if you're going to do a lot of inserts into a compressed table, it's something that you would want to test and baseline. It's just like applying an index. That's what I like to tell folks. It's not a storage setting that you turn on and walk away from. It's something that you definitely want to monitor. You want to try it on, you want to try it off, you want to see what your options are. So if we take a look at the storage engine, if we take a look at SQL Server and we say, okay, a select's going to occur, select's going to come in, where exactly does compression happen within the SQL Server engine? Where does our overhead come from? So we'll have a user query come in. User will contact the SQL network interface, which will actually make a connection via SQL OS, go over to the relational engine. We're going to end up at the command parser. The command parser is going to say, is our syntax correct? If you've ever gotten that nice red error warning, operation error, that's the command parser right there. The syntax isn't correct, it spits it back out at you. We're going to say our syntax is correct. It's going to go, I've got this particular query. Do I have a plan in the query cache that I can use instead of going through optimization? We're going to say no. Guys like Paul White have a great presentation coming up after lunch that is going to deep dive the optimizer. I'm not going to do it justice. We're just going to hit the optimizer. We're going to get a plan generated. That plan is going to get handed off to the query executor. Query executor is going to finish things out by going, okay, I now have a list of how I'm going to get this data. Access methods give me the data. The access methods will go to the buffer manager and say, buffer manager, do you have this data in cache? We're going to say no. No, we don't have it in cache. We can't just give it to you. So what are we going to do? We're going to go over to disk where it is stored in a compressed format. We're going to read it back from buffer manager into the data cache in a compressed format. We're going to go back out to the access methods where the data is still in a compressed format. Now this is very important. All the white papers say that uncompression happens in the access methods, and that is true for page compression. Row compression is actually in a landing pad that's in the relational engine. Because you may sit there and think, when they did the SQL 2005 to SQL 2008 release, how did they have the time to recode the relational engine to work with compressed pages? They didn't. You guys know that records and pages are in a completely different format. The relational engine doesn't care about that. It doesn't know about that. We have to uncompress that data before we can actually satisfy the requirements that the relational engine has to be able to give that back to the user. All that CPU overhead, this is exactly where it happens in this step right here as we uncompress data and we give it back to the query executor. Then we go back to our user. So, nerdy universal communicator equals CPU overhead. This is not from compression. This is from resource governor demo I was doing where I had to blast all the CPUs. But if I showed you a box sitting at idle with like 2%, you'd be like, come on, you can do better than that. But that's exactly where it comes from. We have to be able to communicate with the relational engine and say, here's the data that you need. Doesn't care how it's stored, just cares how it gets it. Scans, updates, and index rebuilds, oh my. We're going to go into this. Updates are bad. Inserts are not nearly as bad, but updates can be very, very bad just because I've hit on a particular bug where as we're inserting data onto pages, it will sit there and it will row compress. If you've already page compressed it, you start getting splits, you start getting fragmentation. If I isolate things to a particular range within one page, I can actually get that to update. I can get it to do another compression attempt. It will log another anchor record up at the top of the page. It will also have the old anchor record at the top of the page. That is by design, because what the team is thinking is, I may have page compressed data that's on this page still. I don't want to uncompress all that data. I still want the space savings that may be there. So even if I go into a page, and I'm going to do it in a demo for you guys, and I say, here's my column and it's all A's. And then I go in and I say, here's my column now, it's all B's. I'm still going to have an anchor tag for A sitting at the top of my page. That will still cause a mid-page split to occur, because even though I've updated all those B's that are on that particular page, there will be a split. I'll get a new anchor tag on top, but that new anchor tag will take up some space that I would have for row compressed records. Updates are just the bane of page compression. If you do bulk inserts and you know that once a day I'm going to load a data warehouse, wonderful. For an OLTP system where you have very, very heavy update operations, don't use page compression on your volatile tables. Just don't. But for anything that you're storing, that you're scanning, once your data gets to be 6, 7 months old and we're just looking at it for reporting purposes, absolutely page compress that. But if we're sitting there updating it constantly, please don't. Index rebuilds. Once we compress everything, we've still got to maintain it. Bless you. You will see your index operations go up. It's going to take a little more time as you index rebuilds. The safe bet is just, yes, sir? Elapsed time, but it will take up more CPU. Yeah, absolutely, absolutely. Yeah. Yeah, absolutely. And I mean, you can do other things, like if it's taking up too much CPU, or if you got other things going on at the same time, you could use max stop on your index rebuild. So, and that's the thing, is there's a lot of ways around this, but just expect that you're going to see more CPU. Expect that any index rebuilds on row compression are going to take at least 1.5 times longer. Anything else is going to take 2 times longer. So as we're talking, scans versus updates. Updates are bad. Yes, sir. You would have to see. It would depend on how much. If you're CPU bound, I would say no. Just because you're going to take additional, because not only do we have to translate things from to the relational engine on a select, on an insert we actually have to translate it to the page compression format that we're going to update in the buffer pool and also to the write-ahead logging. So, yes, yeah, absolutely. So what in the Shire do hobbits have to do with my data? So it's the only Lord of the Rings photo I can figure out how to get in here, and that's just because in-row data is also known as hobbit data. So in-row data is the only thing that compresses. Yes? At 11? How long do we have? Okay. So what we're going to do is, I've gotten up to a certain point with this. I'm going to show you a couple demos. I'm going to go really, really quick, and then and if anybody wants to stick around because it's lunchtime, we can do that. If not, please feel free to get the heck out of here. Like I said, it's a deep dive. Go grab all the demos. Go grab the slide deck. This is everything that you could possibly want to know about the internals of compression. The last thing I want to tell you, we talked about scan operations, so if you want to know what you want to compress on your data, I've got a Monday morning quarterback guide that's on my website. It's basically, if I was going to sit down next to you, here's the steps I would take to see should I be compressing my data. One of the scripts that will be on the next demo is just you scan your database, you can put in your particular tables and find out what your allocation units are. How many pages do you have? Anything that's not an in-row data, you don't want to compress. I've got a demo that I did that's also up on the blog as well. Varchar max data is very deceiving. It starts off as in-row data as long as it can fit on an in-row data page. You can compress that data, and it works there. But it's once it falls off to either slob pages or lob pages, it will no longer compress. I'm sorry? Text data type. So there's still an option that you can store that on data pages. I think that's depreciated in 2012. I know that it was depreciated in 2008 R2. All right. So I'm going to do these two, and then we'll call it a day. And like I said, if anybody wants any more of this, please go out and grab all the different scripts. But that actually pretty much does it for the slides. Where after that, it's just a couple more slides going. Here's more demos, because you could do demos on this until the cows go home. But so this particular one is for scans and updates. So if you go to one of the databases that we've been using, and all we're going to do is look at the sys DMDB index operational stats to be able to take a look at singleton uses. It'll report your scans and it'll report your updates. If you have a high percentage of updates, you would not want to apply page compression. If you have a high level of scans, then that tells you, okay, page compression. But this is something that would help you gauge what level of compression is actually right for my table based on its behavior. Now, for this particular one, what I'm going to do is I'm actually going to create some allocation units for you guys. I've got a table right here, and I've got a varchar 8000, varchar 8000, a varchar max, a text type field, and an integer. Probably not a table that I would want to compress, but probably a table that you might have in your actual system. So let's insert 5,000 pages real quick. Trace on 3604. If we take a look at our table, you can see we've got a lot of pages. And we're going to look at sysdmdb partition stats and sysindexes and sysobjects. You can see here's my table right now. Here's the number of in-row pages that I have. Here's the number of lob pages that I have. So remember, slob data only occurs if you actually update something on an in-row data page and it's updated to the point that it's less than 8,000 characters. So those 8,000 characters and higher would actually go onto a lob page, but slob, you got to be in a bit of middle ground. So I'm going to take my two varchar 8000s, I'm going to update both of them, and I'm going to force one of them to fall out. If I take a look at this again, I can see that now I've got in-row data, row overflow data, and lob data. Now, if I was looking at this table, and I've sat there and I've looked with customers before. I had one customer, they had a 130 gig table, and they said, we want to compress it. And I took a look at it. And they had an integer ID field, and then they had a lob data that they were storing binary files in. And after scanning it, they had about 50 in-row data pages, and they had a couple 100,000 lob data pages. And I said, look, guys, you don't want to compress this. If you try and compress it, you're just going to put overhead on those pages that have pointers to your text files. And what that's going to do is it's just going to add more overhead to your scan operations than you've already got. So this is very, very important. Before you go in there and you just set the setting, take a look at your scan patterns, take a look at your allocation units, make sure that you know exactly what it is that you've got. Know thy data so that way you know how to compress it. Absolutely. So if you were actually doing something where it was file stream data, what you would do is you would take the file stream data and you would probably compress it at the drive level. You wouldn't want to do something like that at the storage level because it's just not going to help you at all. So, yes, sir. It will only do the in-row data, and what you would want to do is you would want to test that, because my suggestion would be don't do it, because that in-row data is actually going to have pointers to your text data, and so you're going to put CPU overhead every time that you've got to use those in-row data pages to get the pointers. So if you're doing scan or seek operations, you're going to add overhead. Now again, this is if you're CPU bound. I've talked to folks before that have said, I have compressed my entire database. Is that bad? Probably. To be honest, probably, but if you don't see your CPU go through the roof and your performance isn't bad, it may be one of those things you're willing to take a hit on. But when you compress, because the page sizes and the record types are going to change, your execution plans will change. So whether or not it's really bad, you could take a query, run it, baseline it, get an execution plan, compress, run it, take a look at your execution plan, take a look at the differences. If you got a better execution plan and things are working better, absolutely. It's just 9 times out of 10 that the overhead involved on the CPU side is going to make it either run equivalently or run longer if you've got a majority of your data in non-in-row data pages. Yes, sir?
Earlier you had a demo where you had rows that were one page.
Yeah.
In that case, is it better to just leave it as row compressed?
It depends what you're using the table for. If you're updating it a lot, I would say row compression. If you're scanning it, then page compression. So, and one more time, everything is up on the resources page. So if you want, please go out there and grab it. And there's a list of links to the different videos, to the different books, to some of the white papers. That's all also up there, so please get it and read to your heart's content. Jonathan Cahias did something on X events. I didn't get to the demo, and I know we're at time. Like I said, anybody who wants to stick around and see any more, let me know, and we'll go outside, and I'll be happy to show you. But the only way to really manage page and row compression is with extended events. Extended events will actually have a bitmap for row modifications. Jonathan covered this in day 28, 31 of tracking. The nice thing about 2012 is that we've actually got a GUI for it where you could set this X event up and you can say, look at live data, and you can actually see your page compression attempts firing. And then you can use the script involved to actually go in there, get that bitmap, and see what's going on. Because you'll get failures. As you insert data, it'll be like not enough records, data changes on a page in order to fire off a modification attempt. Or data has not changed on page, so we wouldn't get any savings by trying to do another modification attempt. So there's a lot of things. It won't fully compress everything every single time. It'll stop and it'll look and it'll go, okay, why are we doing this? And if it goes, oh, we've got new data on a page, we meet a certain set of criteria, we're doing a split operation, well then maybe we've got enough where we could do a compression attempt. It's a very, very smart process. But that way you'll actually know, hey, if I page compress my table and I don't see compression savings, I can use these queries and I can go in there and I can see this is exactly why these compressions didn't help, why it stayed row compressed instead of page compressed. The only thing we log is page compression. We don't care about row compression because it's going to happen every single time no matter what. We don't have to monitor it. We don't have to know about it. It's either turned on or it's turned off. Page compression, though, it can fail or it can succeed, and we have to log why. But, oh, yes, sir.
So as far as non-clustered indexes and compression, any guidance there?
Yes. So with non-clustered indexes and compression, I think it's a great thing, but again, know thy data. If you've got a char column in your non-clustered indexes, if you've got compressible data, you could shrink that. And that could also reduce the amount of time that range scan operations take if you're scanning that data. Remember, the non-leaf levels are going to be, their compression type is only going to be row, and that level of row compression will be completely dependent upon, how full is that object. If you take, you've got the 900 bytes that you've got to fill. If you want to put that on a 900 byte column that's full every single time, row compression won't help you on your non-leaf levels. It probably wouldn't help you on your leaf level pages either. But if it's data types, and I've actually seen people where we row compress non-clustered indexes or page compress them when we don't even touch the base table. And the reason is the base table, it might have some volatile information, but if we scan on something often enough, and we can actually get a really good compression factor off of that, whereas we might not for the table. The example, that document folder. What if I cared, what IDs were in that table, but I didn't care about the documents? Well, I could make a non-clustered index off of the IDs that just had that ID value in there, and I could compress that. And then I'll be able to scan that very, very quickly, but the documents won't do anything for me. Absolutely. So there's a lot of options there. Like I said, compression is a tool to use like indexing. Use it, but make sure that you know why you're doing it. It's not just turn it on and let it roll. Yes, sir.
Is it safe to say that replication needs to be isolated from this?
Yes, if you compress something and then you replicate it, it's not compressed on the other side. Because it's got to come out of the relational engine and it'll be translated at that point in time. So, and even transactional replication, it's read out of the log reader through the distributor, but you're right, by the time that it's up in the distributor, it's abstracted from that. It doesn't care what format the record's in. Good.
It might be a good idea to replicate that even if it doesn't make sense. Your subscriber side, even if it doesn't make sense.
Absolutely, and I actually see a lot of folks that do that. Just because once you get in the reporting data, your behavior's different. But then again, that'll also depend on, you could look at it by table. If you had transactional replication, heavy updates on one side that we're getting over, all of a sudden, your update patterns, when you look at the scan update patterns of the singletons, you'll start to see, okay, this table is too volatile. The best place for row compression is really data warehouses that are loaded once a day or once every so often, to where you can actually plan, okay, I could apply page compression and make sure that I don't get a lot of fragmentation out of it. Because that is the one side effect, is if you apply page compression to something and it's not meant to be page compressed, or there's too many updates going on to where it could actually hurt that, what'll happen is you'll get a lot of fragmentation because of that. Good? Thank you guys very much.